Yeah, sure.
Okay, and I think we are recording already.
Yeah, I can.
Okay.
I
Oh,
can
that
stop.
sounds good. No, we can start,
Okay.
Janine. I can go ahead and introduce Saeed and we can get started. Yeah.
Sorry, I stopped it. I can start it again.
I'm gonna let Darlene take that. Okay, I'm gonna go and
Thank you.
watch from my other side.
I don't think it did stop. Go ahead. It's rolling.
It's rolling. Okay, all right. Sounds good. Okay, welcome everyone to today's ESIC seminar. Today we have our own Professor Lotfifard. Dr. Syed Lotfifard is an associate professor with the School of Electrical Engineering and Computer Science at WSU. He received his PhD in electrical engineering from Texas A&M University. His research interests include protection, stability, and control of inverter-based power grids. Dr. Lotfifard is a senior member of IEEE and serves as an associate editor of IEEE Transactions on Power Delivery and IEEE Transactions on Sustainable Energy. Dr. Lotfifard today will talk to us about fault-resilient inverter-based resources in weak power grid. Back to you, Syed.
Okay, thank you. Thanks for introduction. So, first of all, hello, good morning, and most of you I have already seen, so that is good. So, okay, let's jump into the presentation. So, the topic that I'm talking about today is about the fault-resilient inverter-based resources in big power grid. So, the outline of the talk is as follows. First, I will talk about the introduction and the background and what we are doing as related topic of the inverter-based resources grid integration. Then specifically, I will spend time on the weak power grids and challenges and solutions that we have developed so far, and we can discuss more about the detail. And then I will summarize the talk. So challenges is that, as you know, that we are pushing toward the integration of the more renewable energy inverter-based resources. So inverter-based resources could be in terms of the energy storages, solar and wind, HVDC system, battery storage, and so on and so forth. So the challenge is that, of course, all of them are nice and they are cool, but there are some challenges associated with that. So which are related to operational security. So operational security in terms of the NERC is defined as the ability of the power grid to tolerate large disturbances that could be due to fault, outage of the component, and so on and so forth. So the question is that when we have large integration of the IBRs, inverter-based resources, so we will face by new dynamics compared to the synchronous generator-based power grid and new fault response characteristics that has led to several major outages in power grid. So I have listed few of them, but there are so many more. So for example, in case A, it is the UK's blackout in 2019. Basically, what happened at transmission line and the protective relays at the distribution side, they misoperated and assumed basically that relays were related to islanding detection. So the event at the transmission line appeared as an islanding scenario to the relays at the distribution level. So it disconnected more than expected. So therefore, when they did the unit commitment of the transmission line, they didn't consider this scenario. So therefore, it led to the cascading failure over there. So the major power outages. The same thing, we have seen that in the South Australia blackout, the same thing. Usually that's a mixture of the how the renewable energy have responded and how the protective devices have responded. Because when we do the protection system, basically most of the algorithm are based on the conventional synchronous generator based and how they respond. And they develop the digital algorithm settings and everything based on those philosophies. So then if something totally changes, then there are some relays are vulnerable, some of them are not. So here the vulnerable protective relays have operated. Same thing we have seen in the Southern California, even in 2018, several events at the kind of short period of time. And 7 hertz power and voltage oscillation in first solar in the Arizona, which we will discuss later in this slide in more detail about part B. So then we have so many also, even we have seen in German transmission line due to the the temporary over voltages. Basically, even has happened and temporary over voltages happen and propagated to the system and caused the major outages. Then also we have seen in the 2011 outages in China, wind turbines, wind farms in China. So all of these are really somehow related to either different fault characteristics of the phenomena that we have seen or different control response of the inverter-based resources or combination of these two. So then back to this thing. So what is the need? The need is that we have to develop the grid integration impact assessment and fault resilience enhancement tool to make the more informed integration of this thing. So then in my group and with my students, mainly we are working on the methodology for modeling, analysis, and enhancing the fault response behavior of the system, either at the protection level response or at inverter-based response or the coordination of these things. So the goal is that we want to make sure the system is fault resilient. So therefore, the key focus areas are basically I can divide to twofold. One is that the protection aspects of the problem, how to develop digital relays, algorithms, how to coordinate the relays, how to come up with different schemes. So it could be at component level or system level, or it could be how to reinforce the stability of the grid. Basically, because once the fault happens, first you have to clear the fault. Then once it's cleared, you have to make sure the system keep continuing as before. So basically, that's the main definition of the stability. So these are two main areas that we are working, and I somehow try to explain what are the relation between these two. But for today's talk, what I have decided, I decided to talk about one of the kind of interesting topic that we are working last several years. So, and that is on how the fault response of the inverter looks like and how we can enhance that response in a weak power grid. But before going into the topic, let's define what is the strengths of the system and what do we mean. Yeah, you can see. Oh, you have that one. So how we can define the strengths of the system and what do we mean by system is weak. So there are so many definitions. So basically, there are rich body of the research on how to define the strengths of the system. But without going to the details, let's go by one simple index that people use. That again, this is not accurate index. So you can read so many document reports, and there are so many variations. But if simply we want to talk about that one, basically short circuit ratio is one of the indices. So basically we talk about that. If I want to integrate the renewable energy at certain point to the grid, I should see that what is the short circuit ratio at that point. Short circuit ratio defined by the short circuit capacity at that point. For example, I want to connect that to the terminal T. So I should see that what is the short circuit capacity at that point. Short circuit capacity basically means that you should calculate the fault current at that point and consider normal condition voltage at that point. So basically from that, you can calculate the short circuit capacity at that point. And then you know how much inverter you want to integrate to the grid. So you know the capacity of your inverter. So that's why it's called the short circuit ratio. So short circuit capacity over capacity of your inverter. So by definition, there are so many variation here, but by definition, if your short circuit ratio is more than 5, you're okay. That is a strong grid. If it is between 3 and 5, it is weak system, and if it is less than 3, you are very weak system. So, and this one again, there are so many variations here. So then, what's the relation here? Because the weaker system become your static limit reduces. A static limit means that what is at a static condition, how much you can inject to the grid. So for example, this is the equation. Basically, you have seen in your power flow equation. You can easily derive that equation from your power flow equation. So it's very related to, you see that it is related to short circuit ratio and also the ratio of the resistance to the inductance of the system. For example, here, this is a nice graph. It shows that for different short circuit ratio, you have, and depends on the how much resistance your line has, you have your static limit changes. For example, for 90 degrees, which means that you have purely inductive system. So then you have that red line. So then if it become more resistive, you basically your static limit or the power that you can integrate to the grid increases. So that is, so if in case you are simulating something, to make sure to include that resistance. This is really important when you're working on the, so again, this says if the system is on the weak system, this thing happen. So not the normal condition. But even it is not the binding condition. The dynamic limit is even if it's worse. So basically dynamic limit means that if you have a disturbance in the system, so can you still be stable or not? So there are so many studies have shown that if you go to short circuit ratio of 1, basically you're because of the dynamic limit, you go to less than 40% of your capacity of the inverter. So you have a large capacity inverter, you want to integrate, but because of the dynamic limit of the system, you cannot go more than that one. So if you start tuning the controllers and play with that one, people have seen that even you can go to 60% too, but not more than that. So therefore, the summary is that any solution that you can provide that can enhance the dynamic response of the inverters, it significantly impact the capacity, grid integration capacity of your grid. So you can integrate more renewable energy. So that's why I picked up 2 of the examples of the works we have done last few years on how to improve the dynamic response and fault response of the inverters. So before jumping to the issues, let's see that what is the weak grid, when this weak grid happens. So that's a good question. So you say that, okay, you're talking about weak grid, but what are the examples? I picked a few examples here. For example, one case is that usually wind and solar energy are far, most of the case, sometimes not, but most of the case is they far away from the load center and the residential area and so on and so forth. So you have to bring the wind or solar power from remote areas. For example, there are so many cases in Australia, you can see that. For example, here there is a site, Moselle Row. As you see that is at the top right here, and then you see that to bring all the way from there to these load centers, you have to have a radial transmission line. So therefore, and that is obvious case of if the short circuit happen at that site, for example, here and so on and so forth, then your short circuit reduces. For example, here, based on the study, short circuit ratio at that site is 1.74. Or there is another site, it's called Kennedy Energy Center. So in normal condition, even the short circuit ratio goes to 1.5. This is very weak grid. So even if you take the N-1 contingency, your grid goes to 0.7. So you see that extremely weak grid. Why that's the case? Again, because the renewable sources are at the remote area, they have to bring to the load center areas. The same thing we have seen in Texas. So that's very well-known example. Usually the load center areas at the west, for example, Houston, Austin, Dallas, they are mostly are here at the west side. But the winds are basically at here, that east side. So basically bring from that side to the load center, again, either you have to connect much more renewable transmission line or the controller and or combination of these things. So, but at the present, that area is extremely big. So, and that causes problem. Sometimes the problem is not because the solar energies or wind energies are at the remote area. For example, in the Southern California cases, they are very close to the center of load. But the problem here is that the grid that at the location that you integrate the renewable energy to the grid is the network over there is weak. So basically you have few lines that are connected to the grid. So then, for example, this Tehachapi Pass wind farm in California, this is one of the largest wind farm in the country, and that's the early stages. So you see that it is almost 700 megawatt power by 3,400 wind turbines over there. So again, but that is a big system too. So because again, they are close to wind road center area, but the system that is connected to the grid is weak. Another case is that islanded grid. For example, here is the Mediterranean islands. So these cases that I have picked up because they are report on the characteristics of the grid. Again, this is the island over there. The system is weak. They are not. We don't have a system that connected to the rest of the system. Another example would be when, for example, cascading outages happen, or you do the intentional islanding. So again, that part of system becomes weak. Or when you are doing system restoration, so still your system is not strong enough. So then the system at that point is weak. So that you have to be careful about how you do the restoration problem. Another type of weak system that are even more challenging are that the system at the beginning is not weak, but when the fault happens in the grid, you take out few lines in the system. So then the system becomes weak. And that's the case that I talked at the first few slides that about the Arizona case. So that's a realistic scenario. So they had some event in the system, they disconnected the line, then the system became weak, and the PV farm started showing oscillation, 7 hertz oscillation. Then they did some studies, and they see that even at the weak system, so once they switch to the short circuit ratio of the 4, then the system becomes unstable, and they have to disconnect them. You will see that there are some simple way to address that one, but there are some issues with this one. But right now, I'm just talking about the cases that how the weak grid created. So these are examples. So then again, 2 examples that I picked up today for our discussion are the one is that how to enhance the fault response to the inverter response to fault, and how to make sure the system stay grid synchronization. So grid synchronization of the inverter is another issue. So hopefully we have time to see that. Should I go faster? Probably yes. So these 2 topics, hopefully we can cover that. But if not, we can discuss later on offline. So one is that, okay, what is the inverter? So very simple case. I have just put simple case here. So if you have a PV system connected to the grid, typically, again, this is 2-stage. Again, we have different topologies and so on and so forth. But just you get the idea here. So you have renewable energy, you have the DC-DC converter, then you have the inverter, integrate the renewable to the grid, and you have a feeder to the main grid. So usually when you want to do, and the whole idea here is that you have maximum power point tracking at the PV farm. So basically you decide at which voltage point you should operate, such that you can get the maximum power from the PVs for the given sun irradiation. But your inverter may work at different voltage level, and most of the time it's working at different voltage level. So then what should you do? Basically, you should match these 2 voltage levels. That's why you do the DC-DC converter. So here at left-hand side, you have different voltage, and right-hand side, you have different voltage. So you match these 2. And then the job of inverter is that whatever power that comes in should goes out. Otherwise, the voltage level increases, because the more power comes in and less power goes out, the voltage increases. If the power goes out is more than power comes in, the voltage reduces. So that's a good indication of whether you are injecting the same power to the grid as generated or not. But then typically, this is a very common approach that we synchronize to the grid. So basically, we use PLL, phase-lock loop. So basically, you track the voltage of the system, phase A of the system. Then later on, we will discuss. I have few slides on this thing. If you cannot follow that, that's fine. So we will discuss later. So you should track that one. Then you go to the inverter. So basically you get the voltage of the DC, and based on that, you send this command to the controller of inverters, and in DQ frame, they will inject to the grid. Then we will discuss later on about the DQ frame shortly. So this is basically typical controller of the PV farm. So, but again, to make sure that the grid is working well, especially voltage stability issues. So there are grid codes requirement. You have to inject certain reactive power during farm. So this is the typical curve of the reactive power. So basically means that for each percentage of the voltage that drop at the terminal of the terminal of the PV, you have to inject twice as that one of the reactive power. If you work in the DQ frame, reactive power means you have to inject IQ, so in the system. But again, we will discuss that this is for balanced system. So it is for positive system model. So we will later on, we will discuss what do I mean. One issue that appears here is the saturation of the inverters. So basically when the fault happens, what you are doing, before fault, usually IQ is 0. So you don't inject reactive power to the grid because you want to allocate all of your capacity of inverter to active power. Basically whatever you are generating, you want to integrate to the grid. But during fall, you have to switch to the reactive power injection because you have to follow grid code. If something left, that's fine. You can use for reactive power. But first, you should meet the grid code requirement. So therefore, what happened at that time, your controller may get saturated because you have a large disturbance in the grid. So basically, your set point is significantly changes. So then how to take care of the saturation of the inverter? Because if it's not you don't take care of the saturation, then we will see that there are some problems happens. There are some control theory applications that you can design the controller such that the constraints are already integrated to your control design. But if you follow those, basically, because power grid, we have certain condition and variable limit and so on and so forth, you come up with so much conservative result that even maybe become useless. So therefore, what people do, usually what we do, we design the controller, we ignore the limit, then we apply the anti-wind-up controller to that one to take care of the situation that you take, this inverter becomes saturated. So then the typical anti-wind-up, I have listed few, but there are so many more. So for example, PI, anti-wind-up PI with dead zone. So basically, when it gets saturated at a certain point, basically saturation coming from that integral part. The proportional part is okay. So, but integral part, you have to take care of that. But there are so many different ways. So PI tracking, basically you look at the saturation limit, and based on how much you saturated, you inject the compensation signal to take care of this integral point. The IEEE standard that usually in synchronous generator are used is called the PI conditional. So basically means that once it gets saturated, just don't inject anything. So just switch to 0. So if you switch to 0, so then it's not, your integral does not accumulate anything. What do I mean by that? So basically, when it's saturated, doesn't matter how much you inject. If the limit is 10, it's remain 10. So therefore, your error keep coming back to your inverter, the controller. So and your integral part keep accumulating that error. So that's the problem. So therefore, you want to get rid of that one. So, but these are the problem here with this thing. All of them are heuristic approaches. So basically, there is no solid rule over there to go through. There are people came up with some rule of thumb how to do that. But there are so many reports here and there that say that, okay, this is the problem. They have proposed some ad hoc solution to, for example, this one, that PI conditioner, which is mostly we use that one. So then, for example, if you use this one for motor drives, based on the dynamic of the motor, you see that during time that is saturated and you switch basically to do nothing and then coming back out of saturation, there's some condition happen in the system. So therefore, it cannot track that. There are so many approaches to want to modify this. Why? Because the whole thing is heuristic approach. And I said that why we go through that, because that's the nature of the problems that we are dealing with. So then what we did, we used some controller, basically is used, basically developed by different group in Japan. So what they did, they called it the proxy-based sliding mode controller. Sliding mode controller is a nonlinear controller that switches between the limit that you have, and PID is a controller that we are using. So they combine these two strategically such that you can basically you can check how go from the saturation point to post-saturation point. So that's and there is a rich theory over there. So you can exactly, you know what you are doing over there. So I don't go through the detail of the controller. So, but basically these two videos that they put on their website, that is nice representation of this one. And if it works, hopefully, yeah. So you see that PI try to track that red dot. You see that? Once the person grab that handle of the robot, so basically like you saturate that one because you put the, so you see that then it's difficult to track that one. So that's the problem happening in Power Grid 2. So you see that? That right now it's saturated. So, but if you look at this one, so once they grab the arm, so that you see that without any overshoot anything, it just suddenly goes to that one. So that's the basic advantage you see here that they had different applications. But for us, the application was for Power Grid. So for example, here you see that if you have a step change, you have different overshoot for different cases. So this is for typical, you just use the one transfer function. It doesn't represent anything. We just wanted to see that how the controller are responding. So that black one is a proxy-based sliding mode control. So you see that it shows better response. But later on, we will see that right now, maybe that's not a big deal in this figure because we haven't put in the control loop. So if you put this thing that in inverter that are related to other stuff, you will see that the problem shows up. So here, for example, this is the controller. We put it here because here is the most sensitive part. So basically, it's the part that you switch from ID injection to IQ injection. So that's the part you really see the difference. So, and if you see that, for example, if you don't follow, this is extreme case. I just wanted to show what happened. So if you don't have those anti-wind up cases and so on, see that how the inverter will respond. But if you have any anti-saturation issue, so you see that you follow other one, that is smoothly go to the post-fault condition. But how you go to that one depends on how you implement your anti-wind up characteristic. So, but before I go there, so the main issue was that here we showed a three-phase system. But this controller is not good for asymmetrical fault. When we have, for example, single phase to ground, two phase to the line to line fault, line to ground fault, and so on. This is the here we had three-phase fault. That's why we didn't have any issues. But if you go through before I go through the whole thing, so those of you that are not familiar with DQ frame and so on and so forth, hopefully these two slides clarify that. Let's assume I apply the three-phase voltage to the system. So that is the balanced system. You see that phase A has certain phase, the two other phases have 120 degrees phase shift. So if I do the Clark transformation, so what happened? Instead of three-phase system, you will have two components, alpha and beta. That is called Clark transformation. But then if you see that, you get a vector that rotate with the speed of omega here in counterclockwise. So then if I apply to the Park transformation, what is the Park transformation? Basically, if I apply the Clark transformation to the controller, so you have a vector that rotating by a speed of omega, then tracking that one would be difficult. Basically, even you cannot use PI controller because you have a rotating, your reference is changing and you cannot track that one. But the Park transform, Park said that, okay, let's move, if I move the coordinate here with the speed of omega, the relative speed becomes 0. So because if I rotate alpha and beta with the same speed of that omega, then the relative speed becomes 0. That's why this coming to the play. So therefore, you get two fixed numbers. Then this thing is easy. I can give it to PI and it track that easily because that's a fixed number and we can follow that. So, but the question is that how do you track that one? Then again, that is simple. So if I track this, I rotate this alpha and beta with the speed of omega such that my phase, I get locked to the phase A, I see that VQ becomes 0. And that's why it's called phase lock loop. So basically you track the phase of phase A. But basically just assume that Q becomes 0 and just put the PI controller over there and you track that one. Once this Q becomes 0, you have tracked that. So if any disturbance happen to your system, again, this thing will track. This is very simple definition of the DQ frame transformation. But let's assume I change the position of these 3 phases. So for example, I switch phase B and C. So basically, what does it mean? It means that I apply negative sequence. So for example, if you have induction motor, when you go to the lab, when your instruction doesn't watch you guys, so just switch this position of 2 phases. You see that the induction motor start rotating opposite to the direction of the, if you put the ABC. So that's called negative sequence. So basically, sequence is negative. And what happens? Again, I apply the clock transformation. But here you see that omega goes clockwise, opposite to this one. Then I apply the Park transform. I track that one. I get alpha beta. But if you do so, you see that the theta double star is minus of theta star. And it expected. Why? Because this guy tried to track this vector that goes to the counterclockwise, but here you're tracking the vector that goes clockwise. But why I brought up all of, so far what I did in the previous cases, we ignored this part. We just talked about this part. So we assume that every system is balanced. That's why we had that simple case. But why I brought up this thing, because when the fault happened in the system, we have unbalanced condition. So then what happened? You have 3 components: positive sequence, negative sequence, and zero sequence. But the way your transformer of inverter are connected, you don't see the 0 sequence of the grid at all. So basically what we do, we just work about the negative sequence and positive sequence. So therefore we have positive sequence, negative sequence, and how do they look like? It's like you have applied combination of those 2 vector that I talked in previous case. So then the question is that, okay, what should I do? Which one should I track? If I track this one, what should I do to this one? If I track this one, what should I do this? So therefore, let's assume I track the positive sequence. So if you do multiplication, you see that you're good. So you have 2 constant value, VQ plus, VD plus, and VQ plus. But then you have a component that rotates with the speed twice as the nominal frequency because of that negative sequence. If whatever I have picked up, I multiply by negative of that one, I'm okay as far as negative sequence goes, but the positive sequence appears. To solve this problem, what I can do, simple case is that I put a filter and just say that, okay, if I just filter out this component, low pass filter. So then I get this pure fixed number. But the problem here is that because the frequency is so low, so the delay of your filter becomes so huge that you cannot track the system conditions. So therefore, that's not what in power system people do. The very common approach is that you cancel out the component. Let's see that how much time we have. Oh, I have to go fast. So we cancel out those things. So basically we get DQ and so on and so forth. Then we track the PLR at the positive sequence. So then, but another problem with this thing is that how do you observe the value? So if you do the calculation instantaneous power, you see that, again, you have second harmonic oscillation in the system. So therefore, there are so many controllers that they have different objectives. Some controllers are suppression of this oscillation. Some people try to suppress the active power oscillation. Some people try to reactive power oscillation. Some people try to suppress the negative component of the signal, and so on and so forth. But the most common one is that you get rid of the second order harmonic of the active power, because it affects your DC part and so on and so forth, which we don't have time to discuss. So then if you do the calculation, so basically you come up with so basically you see that the objective is that you follow the P and Q reference and make the oscillation in power, active power 0. So then, therefore, what should you do in addition to the previous case? You have to add negative sequence component as well. So that's what is called dual controller. So you not only control the positive sequence, but negative sequence as well. Then here, things become a little bit more complicated. You have to go through different way of determining the settings here and so on and so forth, which we will not discuss that one. So here, for example, you see that if the fault happened, these are the oscillations that you see. If I follow the previous case, that is just positive sequence. But if you go by the double frequency, you see that the frequency are purely canceled out. You suppress that. And here we have applied different type of the anti-binder, and you see that proxy-based controller, you see that after fault, it settles down as fast as possible. So you don't have that as oscillation. But the problem, again, you imagine you have so many of these things in the grid. So if you don't suppress that one, the problem shows up. So that's how you improve the one approach of improving response time of the response of the inverter to the fault. But the second case that, again, related to the same thing, but I will go really fast because we have just how many time? 10 minutes? Yeah, we have just 10 minutes. So this is the synchron. So fault has happened. Relays have cleared the fault. Your inverter seamlessly has gone through to post-fault condition because of those saturation cases that you took care of that one. But the question is that, is my system stable? Can my inverter keep continuing to the injecting power to the grid? Especially we know that the condition that the system become weak. So let's see that. And that is the same case that I talked about. These are the right-hand side is actual recorded waveform I took from some papers. So that's what happened. But the left-hand side, the study that they have done. So, and if you see that if it goes from to short circuit ratio of 4, they have to disconnect. So here we have done simulation here. So for example, this is the multi-machine system. You have 2 synchronous generators, 1 large inverter over there. And to simulate the weak system, we take out 1 line out. So what that is basically shows the large portion of the grid. So once you get it out, suddenly your strength reduces. Before this event, the system was strong enough. But once this event happened, the line goes out. So therefore, what happened? See that we have a simulation here. So once this goes out, the oscillation happen and become unstable. But I can do a trick, and this is because of our PLL are so fast. Those that one wanted to track that. I can make it slower. If I make it slower, you see that the system stays stable. It doesn't become unstable. But what is the problem with this? Again, your PLL is so slow. So therefore, if there are large changes in the grid, for example, if your frequency changes fast, you cannot track that one. You know that because that PLL whole job was that track the angle. So that's the problem. And there are so many events that's happened. So PLL could not track the angle. So therefore, you don't want to go too slow in PLL. And of course, you don't want to go too fast. So therefore, what is the solution? So here, we work this thing in my group. We are working on this thing for the last several years. So with so many collaborators and so on and so forth. What we did is we have done for grid following and grid forming inverter. We said that okay, that's the inverter. Can I inject additional signal? So it's like we call it supplementary controller, like the PSS-like control. If you taking courses on dynamic system, you know that what is the PSS is, power system stabilizing. So somehow similar to that one, we said that can we inject 2 additional signal over there, such that at a steady state we don't touch the inverter response, because the inverter are dispatched based on the group control, and you don't want to mess up with them. So that is, otherwise everything changes. But can you take care of the high frequency component that you have in the system during transition? So that's the whole idea. So that's coming to the play. So then what should you do? Then you have to write the dynamic of inverters. And then you assume that, okay, every signal that I have has two components, high frequency component and low frequency component. We call it delta omega for high frequency component, omega 0 for low frequency. It doesn't mean zero frequency. It could be low frequency component. So therefore, and then if you put it in the equation and do the decomposition of the equation, we don't have time to go through that one. So then what you get a nonlinear equation based on your high frequency component. Then right now I can work on the high frequency component. And we have done nonlinear controller based on the interconnection damping assignment passivity based control. So that is a nice controller. You can work with the system when number of states are high. For example, here right now I have 5 states. So that is difficult to work with conventional nonlinear controller. So then here, then what we have done, the controller is designed. You can refer to that paper that I have put at the bottom for details. But let's just see what is the final result. The final result is that I have 2 additional signal goes to your inverter. That's supplementary control. At the steady state, these 2 become 0. So therefore, it's like your inverter has not changed at all. But during transition condition, you have this high frequency component injected into the inverter. You get your signal, you go through washout filter, you take out the high frequency component that you want. Then give it to the controller, it gives you those values you inject there. So, and that's, for example, here one simulation result we have. If I have the same case, you see that that green one become unstable as soon as you take this one out. But that blue one, you see that that is solidly stable. So you see that just after that there is no oscillation. Why? Because you designed that to be like that. That was a grid following converter. Why? Because you had PLL in the loop. But if you take the PLL out, so it's called grid forming. Sometimes, what is the whole point of the PLL? You track the frequency of the grid and the angle of the grid. But if the grid does not have frequency, what do you want to follow? So for example, you have microgrid. Basically, you should inject the frequency that you want. So that's called grid forming inverter. So therefore, grid forming inverter, there is a famous controller, it's called the synchroinverter controller. So it's trying to mimic what the synchronous generators are doing for inverters. So this is the convention, this is the structure of the controller. Then we said, okay, can we do the same concept here? So then what we did is say that, okay, let's inject additional high frequency component at the voltage level. Because you know that, for example, PSS in traditional synchronous generator, you put it at the voltage loop. No, you don't put it at the power loop because you have the prime mover response and so on and so forth. So then we put it here and we design for this one. So therefore, again, you have to write down a state space model of this controller, then decompose the frequency to the high frequency and low frequency, and then plug in the equation and to come up the equation for disturbance or perturbation that you have. Again, that is nonlinear equation. So that, for example, here x1, x2, that's a multiplication of states. So that's nonlinear equation. So then we design nonlinear controller for this one. So that's the way it does. So we take the signals, go to washout filter, we take out high frequency component, give it to your controller, and the controller calculate how much additional signal you should inject to the inverter. And again, the beauty of this is that at the steady state, this signal is 0. So therefore, you don't mess up with your controller at all. I mean, that's the whole point. So otherwise, we could simply throw away this controller and design another controller. But we didn't want to do that. We just wanted to keep it there because there are so many reasons why people have gone through that. So we just take care of the weakness of the controller, but the strength remains there. So for example, here we have done for the microgrid. The microgrid is also another good example of the changing of the grid strength. So if it is connected to the grid, it's a strong grid. But if you go to islanded mode, then it is weak grid. Because you have just few inverter inside, you know that's the problem with that. So then the same problem, you see that if this transition happen, if you don't use our controller, you have those oscillations. But if you use our controller, that green one, you don't have any oscillation and go to the post-fault condition. For example, it could be due to fault happening in the system, you islanded the inverter. So I think, yeah, we are in good time. So the summary is that as more inverter goes to the grid, there are so many challenges shows up. One of them is operational security, which for no reason I'm so much passionate about that one. So we try to solve those problems, and there are interactions between the protection issue. The slides, I didn't talk about protection at all, but if you are interested, we can chat offline. So the protection issue and control, and how these two interact with each other. So in this slide, I know that I went real quick over everything, so hopefully you could follow that one. So we talk about the two aspects. One is that how, if the fault happen, how to make sure the inverter inject reactive power as expected by grid code and go seamlessly from during fault to post-fault condition. And then the second part was that once you transition to post-fault condition, how do you make sure that the inverter remain to the grid and follow what inverter is supposed to be? So these are two aspects we discussed in this slides. And the final thought is that you have, again, some of you, I see the faces are scared, don't get scared. So we have so many problems, operational security, and that is actually nice. That makes us busy. So we have so many problems to work on. But as you see that, for example, here I put the computer chips at the 1970s. So that was like that one. But they have worked on that. And right now we see this. So I'm sure that in the next few years, we will overcome all of these challenges. And so many of them are already addressed. Some are still there. And I'm sure we will come up with so many interesting solutions. So, okay. That's my talk. Any questions?
Thank you, Saeed.
I hope I didn't go over time. Good. Yeah, I have 10 minutes.
Right on time. Thank you so much. This was a very interesting presentation.
Sure. Thank you.
I'll open it up for Q&A. So let's see if we have anything on chat. And please feel free to raise your hand online if you have any questions. And we can start with students in the room itself.
Thank you for the talk. Just wanted to know the initial part of control, like the basic control is done in frequency domain. Once you convert it into DQ, then you do a frequency type of control with PID control. And then you go into issues with, what was it, integrator winder. I want to understand why don't, because then you transition into doing nonlinear control with full state feedback. Why not do the same thing over here? Why not do time domain control before? Just wanted to know why is it still in frequency domain? Is there any?
You're talking about the anti-wind-up case or the second part, the supplementary control case?
So if you can go back to the slide.
To the part transformation things? Let me go back to see.
Before that. There we have the inverter control slide.
Oh, the first things, the first slide?
I think, yeah,
This
that is
one.
good. Over there. So over here we have like measurements coming in as 3-phase. We convert it into a DQ transform. We have the PLL. And then once we have all those measurements, we utilize a PID controller, which is frequency domain control. I'm asking, can we have a time domain controller? Can we have a full state feedback over there, rather than just have?
You can do that. So if you want it, yeah, that's what people are doing. So there are so many controllers. They just go by the. Actually, that's good question. So there's actually one topic we are working on. So basically, this one is MIMO system, multi-input, multi-output system. So basically, you have DQ, there are 2 inputs, and you integrate. And what this guy does, determine VD and VQ of the filter. So basically, you have 2 outputs. If you want, you can design the any MIMO system that you want.
There is
So
no control. I just
yeah,
want to
yeah.
understand.
So
there is no
the
control.
issue is that conventional, what we do, we take out this coupling with this omega F. So you get to 2 C's of control. Then people, because people are more comfortable with PI control. This is conventionally in use in power grid, and there are so many advantages to that one. They are robust, and you can have so many things. So that's why people still stick to that PI controller. But there are so many algorithms, they go by any other controller there. And they have shown there are so many advantages over this thing. But traditionally, because the PI controller is used in power system, that's why they prefer this one. But if you don't like that, that's totally fine. So, for example, some people, even they don't go to this negative sequence and the positive sequence. They say that, okay, what's the problem with PI? You have to track the constant fixed number. But they say, okay, there are some other controllers. They have perfect tracking performance. Why we don't use those things? So therefore, even drop this idea. They just go through that. But the problem is that, okay, so you have to train new people that learn to work with those things. But PI basically, you already have workforces that are comfortable. So there are more kind of logistic parts rather than theoretical aspects.
Like it's just comfortable and,
sure, yeah.
and people
That's
can do it. And other
Okay,
question
so
Sure.
sorry, I think we'll come back to you, Ninad. So I think we have a question online. Hey, hi, Robin. Good seeing you. Please go ahead. You can unmute yourself and.
Yeah, Saeed, congratulations. It's a very clear and very timely presentation. So I have 2 questions. It seems that we can approximate large interconnected grids by boiling it down to simple equivalents with positive, 0, negative sequence reactances. So can you comment on how appropriate that is and how general purpose that is as the topology changes? And then can you comment on how you're actually doing the simulations? And I've seen people even running the PSCAD and in parallel with lots of different equivalent. Talk a little bit about your computational tools and how to address that, please, as well as how good an approximation can we get with these equivalents of the grid?
Thank you, Robin. First of all, that's nice hearing from you. That was excellent question. So yeah, so first let's go to that equivalent. So the equivalent system, actually we don't need that. So in the controller, so you're talking about this simple case that we put there. So for the controller design, we don't need to know anything about the grid. So that's not we work on the equivalent. But that is just for the simulation case, to just show the condition of the weak grid. But if you want to go be more realistic, so you can simulate larger grid. But as far as we show that, basically we wanted to show we had 2, even some people, they just simulate the single machine to infinite bus. But here we had 2 objectives. One, we wanted to make sure that we see the impact of the synchronous generator at the steady state, because they have also droop control too. So therefore, we wanted to make sure the frequency of the grid is changing. 2 is that we wanted to make sure that we can create the weak grid at the terminal of the inverter. So that was basically these 2 main ideas. So therefore, as far as you can create that scenario, we are good. But once it gets to the controller design, we don't look at those things at all. We just take the measurement and take the DQ frame out of that one. So that is basically respond to that cases. But as you said, that of course it's always better to test in larger grid and see that maybe something we have not observed there, it shows up. But so far we were basically focused on these 2 aspects. And about your second comment, which was about the simulation toolbox that we use. This simulation was based on the MATLAB Simulate, but we also have as ongoing projects, we are simulating everything in PSCAD as well. So I didn't put the result of PSCAD because it's not complete yet. And so far, these 2 perfectly match each other. So we haven't seen any problems. because we wanted to work on time domain. So yeah, these are the two responses. Any other question about this thing, Robin? So is it?
There was an incident in the latest PES magazine where I think it was I don't know if it was, I think it was a wind farm in China that set off subsynchronous oscillations with a steam plant like 100 miles away. Can that also be handled with a combination of single frequency grid models as well as electromagnetic transient IBR models, do you think?
What I have seen that, because they have done for those subsynchronous cases, there are so many cases. One is that they interact with the series capacitor in the line that they have. But also they have some cases, they have shown that even the controller of the inverter can affect the response of the system. Yeah. So for that one, you have to have detailed model of the wind farm or PV farm. Actually, for them, that was, I have seen such a study. So I'm not sure exactly the one that you are referring to, but I have seen so many recent studies and they showed that one. But basically they showed you have to have a detailed model of the wind farm. But here we didn't have that one. So if you look at here, for example, where is that? Oh. So the whole PV farm is just one IBR. So yeah. Actually that is interesting comment that you mentioned. Basically right now we are working on that problem. So you see that in reality, you don't have one large inverter connected to the grid. So you have so many smaller ones. Then you have a feeder accumulated and then integrated to grid. So then we wanted to see, we are working on that one, see that what happened interaction inside the PV farm or wind farm happens. Here we haven't captured that one yet. Yeah.
Thank you.
Yeah, sure.
Thank you. All right, back to students. Yep.
Okay.
Go ahead.
In slide 14, when you're talking about the response to symmetric fault, you mentioned something about matching the voltage of the PVR into the inverter. Like, is that for?
Yeah.
Yeah.
Mm-hmm.
Is that for grid forming alone, or both for grid forming and grid forming inverter?
This VDC. That's how you usually grid forming. You go by. Usually grid forming. You go to the voltage source converter. So basically, this part, the left-hand side, somebody else should control the voltage of DC here. So, but here is different. This is PV form. So therefore, DC controller is job of inverter. So, but I can switch this. Who should stabilize this DC voltage? I can put it the left-hand side or right-hand side. It depends how you do that. But for PV, the objective is that I just inject whatever I get from the sun to the grid. But I can put another, for example, battery here or fast responding resources here and assign this voltage stabilization to that component. And then free the inverter for frequency stabilizing and so on and so forth. Voltage, frequency, whatever objective that you have. So yeah, therefore you have to differentiate to how people use the DC. That is interesting comment. So usually when people study that one, if you look at papers and so on and so forth, the whole DC part is modeled by one fixed voltage DC here. What does it mean? They have ignored the impact of the DC component. But if you factor in, there are so many interesting things happen over there. So here I have shown the full schemes.
Dr. Lotfifard, so it's a generic question. So what kind of grid model do they use for calculating SCR? So what do they just use the Thevenin equivalent and calculate the short circuit capacity at that point, or how do they calculate SCR at a grid point?
The one way is that you calculate that one. We wanted to show how the relation to it, but you can run the short circuit program and see that what is a three-phase fault at that point. Once you have the current of that one, so this is the I fault, and then you know the nominal voltage at that point. So S short circuit is square root of 3V times I. So therefore you have that S. Then you have this S of the inverter that you are integrating. So then the risk ratio becomes short
So
circuit.
it's the whole network model that we need for calculating SCR.
Yeah, you have to consider all the synchronous. That's why, for example, n-1 contingency, what happened if you take, for example, one generator goes out, your SCR reduces. So that was, it's not fixed, so it depends on what kind of contingency you are.
So you shown the oscillation frequency to be 7 Hz. Are there any higher frequency observed? And does those oscillation frequency affect the strength of the grid?
Yeah, those oscillation, if you don't damp them out, it may become the whole system, system does not become unstable. You have protective devices that disconnect this one, or you reduce the injected power. So, because what was those things? So if you look at your stability equilibrium in back your undergrad, you see that they are basically at the limit. So that's why they oscillate, and they are not damped out. So therefore, one issue to take care of that one, reduce the injected power to the grid. That's why I said that in some cases we cannot go more than 40% of capacity of the inverter. Because if we go more than that, then the oscillation happens. So therefore, that's one way is to, if you don't do anything, it may trigger other things, and then the whole thing become fully unstable. So therefore, you have to take it out or do something. What they did, they haven't reported. They just said that we have tuned the controller of inverter. But I can guess, I don't know that, but I can guess probably they played with the PLL of the inverter. So if you make it a little bit slower, then you don't see that problem. But the problem here is that there is a limitation how slow you can go. So that is the whole issue of it. Either you should reduce P injection, make your inverter slower. Yeah, basically that is. Otherwise, you have to disconnect that.
All right. Thank
Yeah,
you.
sure.
It was very
Sure.
engaging discussion with students. Thanks so much, Said, for the presentation today. And we'll adjourn for the day. Let's thank our speaker again. And thank you everyone for attending this seminar. Have a great day.
You too. Thank you. Thank you.
Thank you. Bye.
Bye. So what should I do? Should I